Good evening, students. My name is Devanjan De. I am an alumni of BPPIMT from 2018 batch. I am going to take a class on AVL trees. It is a popular data structure used in computer systems. So let's start. Before going to the main topic, let us recapitulate some of the things that we have learned earlier. The first topic is, what is a tree? Now, according to Wikipedia, a tree is a widely used abstract data type that simulates a hierarchical tree structure with a root value and subtrees of children with a parent node represented as a set of linked nodes. So, what is a tree? It's a abstract data type, means a model. It will have a set of operations that we can perform, and it can be used to model some kind of relationship in form of an hierarchy. For example, a parent-child relationship, a senior-junior relationship, and so on. For example, if you want to represent the employee organization in a company, then you can use a tree. So in this case, you will have some boss at the top level, then under him you will have some managers who are working in respective departments, then under a manager you will be having some employers who will work on projects, and under him you will have some employees who will be working on the project assigned by the employer. So this is a hierarchical relationship, and it's an example of a tree. Now a tree in computer system is similar to that of a real life tree, but the difference is a real life tree starts from soil, which is at the bottom, and then grows upward, and a tree in computer system starts from the root node, which is at the top, and then it grows downward. And if you have a tree where the nodes have either no children or one children or two children, it is called a binary tree. So a binary tree is a tree where each node has at most two children. So the example we have given, it is a binary tree because the nodes have either no children or a single children or two children. So this is an example of a binary tree. Now let's remember what is a binary search tree, which is a BSC. So a binary search tree is a rooted binary tree where all the nodes of the tree follow these properties or restrictions. The value of a key on any node of its left subtree is less than that of the key on the parent node. The value of key on any node of its right subtree is more than that of the key on the parent node. It may also be equal. Now, what do you mean by these two properties? For this, we have to see the next slide. Now, see, this is an example of a binary search tree. Here you have the arrangement of nodes in such a way that these two properties have been satisfied. Now here you see the root node, which is 50, and now see the left and right subtrees of 50. Now you will see, if you check all the values of the left subtree, you will see that all these values are lesser than 50, and if you see all the values at the right subtree, then you will see that all these values are greater than 50. So in the left subtree you have 9, 12, 14, 17, 23, which all of these are less than 50, and to the right you will see 54, 67, 72, 76, all these are greater than 50. So now this property not only stands for the root node but also for any other node. So if you check the node 17, then you will see that it has a left subtree, which is this part, and the right subtree is this part. Now if you see the nodes at the left subtree, then you will see that 9, 12 and 14. So all these three elements are lesser than 17. And if you see the right subtree, then you will see 19 and 23. So all these are greater than 17. So this also satisfies a property of BBST. And similarly 12 also follows this one, because left side has 9 and right side has 14. 23 and here you have only left subtree, which is 90, and at the right subtree we have 72. Now the left subtree consists of 54 and 67. So these two are less than 72, and the right subtree has 73, which is greater than 72. So similarly you can check and match the property for all nodes in the tree. So it's a binary search tree. And one important feature of the binary search tree is that the in-order traversal of the nodes of the tree will return the key values in ascending order. Now what does that mean? See here. For this binary search tree, we can perform an in-order traversal. What we do in in-order traversal? First we find the leftmost node, then the root node, and then right node. So we can do a in-order traversal for this tree. So for this we have to first find the leftmost node. Now what is the leftmost node for this tree? Here it is 9. So as per our algorithm, we first report 9. Now after this we have to find the root node of this particular subtree. What is the root node? 12. So we include it here. Now then we want the right node, which is 14. We have included here. Now after this we have to consider the whole this whole subtree, starting for with 17 as the root node. Now we have reported the left subtree. Now we want the root node, which is 70. So we report 17. Now we have our turn goes for the right subtree. Now in right subtree we start with the leftmost node. Here it is 19. So we have included 19 here. Now after this there is only one node, which is 23, and we have included 23 here. Now after this we have to report the root node of the whole tree, which is 50. Now 50 is included here. Then we come to the right subtree of the whole tree. Here also we have to start with the rightmost node, leftmost node. So here in the for this the left subtree is this one, 54 and 67. Now in this whole subtree there is no left child, so we start with the root node, which is 54, and this is 54. Now after this we have the right node, which is 67, and we have included 67 as well. Then we have we want the root node of the right this particular subtree, so which is 72, and we want 72. We have included that. Now finally we include 76, which is the right node of. Now we finally have this whole set of reported nodes, which is 9, 12, 14, 17, 19, 23, 50, 54, 67, 72 and 76. Now isn't this a shorted sequence of from numbers? Yes. So we can say that the in-order traversal of a binary search tree will report the nodes in shorted order, and this is applicable for all kinds of binary search. Now, why it is called the binary search tree? Now, first of all, the arrangement very much resembles a sorted array which undergoes binary search. Now, to understand this, we check the next slide. Now, here you see, this is also a binary search tree, and here we perform an in-order traversal of this tree. So what is the in-order traversal? What is the leftmost node here? 1. And after that we root node 5. Now, and then after this in the right subtree we have to again find the leftmost node. So leftmost node is 7, and then the root node is 9, then the rightmost node which is 12, then we come out again which is 15, the root node of this outer subtree, and then we have traversed this part. Then we have 20, then 25, and 30, and 40. Now we have performed an in-order traversal. Now for example, we have to search for an element in the tree. Let's say the search element is 7. So how to perform a search in BST? We have to compare the search element with the elements in the tree. So what is the root node of this tree? 20. Now compare this 7 with 20. We see that 7 is much smaller than 20. So our search path will go to the left subtree. Now in this subtree we see that the root node is 5, and 5 is lesser than 6. So we have to guide the search tree to the right side. Now here the root node is 15 and 7 is lesser than 15. So we again go to the left side. Now here we also have root node 9. 9 is greater than 7. So we again go to the left side. Now here we see 7. So 7. So we report that 7 is there in this tree. Now they have given the steps also, how this is going. Now let us assume that all these elements were somehow stored in an array. You know array, and the elements are stored in this in-order traversal way. So what we have seen that if we perform in-order traversal here, then the list will be shorted, and here we have got also such an array. So this is the shorted list of elements in the tree. Now let us do a binary search on this array with the search element 7. We can do so because the array is sorted. Now for this, first of all we have to find the middlemost element. Number of elements here is 10 and the middle position is occupied by 12. Middle position is 5, so here fifth starting from 1. Fifth element is 12. So, and we compare it with 7. Now 12 is greater than 7. So what we do, we have to consider some elements for the next iteration and discard the rest. So as per the binary search algorithm, we have to consider this half of the array, and we can discard the second half. The search element will not come in this second half. Now considering this first half, we have to again perform a comparison. We have to again find the middlemost element and then perform comparison. Now what is the middlemost position? Here the number of elements is 5 and 5 by 2 Generally it is 2.5, but in completed division we just ignore the decimal part. So here it is just 2. And what is the second element here? 5. And 5 is lesser than 7. So what we do here? We have to consider the second half of the array. 7, 9 and 2. Now in this array we have to again find middlemost position. Now what is the middlemost position? 3 by 2 by following same logic, it is 1. Now what is the first element here? 7. And we compare it, and 7 is the answer, correct answer. So we have concluded that 7 is present in the binary. Now see, don't you think that these two processes, the process of searching for 7 in this binary search tree and in binary search process, they are more or less similar, if not exactly similar, but there is a similarity between them. Here also we are comparing with some element based on some criteria, and here also we are comparing the search element with some element based on a criteria. Here the criteria is the middlemost element, and here the criteria is the tree criteria is based on the tree position. So the searching in this kind of tree resemble very much with that of the binary search process. So selection of a particular subtree for searching a key. Now in this process of searching, if after comparing such element with an element, if we see that it is much greater, then we have to consider this left subtree and we can ignore the right part. And if similarly if we find it is lesser, for example we had 5, then we have to search for it in the right side. So and ignore the left side. Here also, once we have got that 7 is lesser than the middlemost element 12, then we have considered only the first half of the array and ignore the second part. So here also we are ignoring some thing. So isn't this condition fulfilled? Selection of particular subtree for a searching a key is similar to recursively selecting a division of a sorted array to compare elements and continuous binary search on the selected division. So there also we are considering and ignoring others, and tree comparison also we are ignoring others and considering some new. So that is why it is called a binary search. Now let's see the next point. Similar to binary search, searching for an element in a binary search tree takes O log n time, where n is the height of the tree. Now see, in binary search what we know, the time complexity of this search, the time complexity is O of log n, because each time the array is divided in 2 parts and we perform search on one up only. And in tree comparison you see, here also we consider one part and discard other part. So here also we are only using a fraction of it. So here also the search complexity can be said in terms of log n. Now the search pattern for tree will be slightly different from binary search tree, and that is because of the arrangement of nodes in tree. Now see, here you see the left subtree is a bit heavier than the right subtree. So you can say that more number of elements need to be compared in this side, but in case of binary search, you can say that only exactly half of them will be used for the next iteration. But here, but in tree search, that depends on whether the left subtree is heavier or lighter. Here the left subtree is heavier, so here it is taking a bit more time. Now, what is the problem in a normal case? Now, as we have understood that the structure of BST heavily affects the height and the time taken to search for an element. What we have seen in the previous example, that the search takes more time in the left subtree because the left subtree has more number of elements than what you can say the half or ideal situation, or more than the half of the total number of elements in the list tree. So here it is taking a bit more time. Had it been had the search element been 30, then we have needed not 30, 40, then we could have done less number of comparison, because the right subtree doesn't have much number of nodes. So we can assure that search time in a tree is highly dependent on the height of the subtree on which it is performed. So if it is lesser, then the time taken will be less, and if it is more, then the time taken will be more. And the next point says the exact same thing. Depending on the order of insertion of elements, a binary search tree may take a skewed form. That is, the size of one subtree may be much larger than the other. So here also you are seeing the left subtree is heavier, and this occurs based on how we are inserting the elements in the search tree. So for example, had you inserted 7 before 15, then you should have some other structure other than this. Now this is still what you can think that this is normal. Here also you can see that 20 is the largest element in the tree, but it is only inserted at the beginning, so it is the root node, and the whole tree is skewed towards the left. And after this they have probably inserted 19, then after that 8, then 15, so on. So had they inserted one first, then others, then you could have a right skewed one. So that all depends on how we are inserted. Now nevertheless, the main problem where we arise is that the search time will also gradually increase. So if we want to search for say 13, then we have to compare more number of elements, 19, 8, 15, sorry 15 not included, 8 then now here 8 then 13, but it would have reduced. Now by searching, the time will approach O of n. Now had it been 1, then that would have been a case, because you have to compare with 20 also, 19 also, 8, 2, then 1. So we can discard only 2 elements here. So time has increased much. Now we have to see the worst case here. Now for as I told earlier, that if 1 was inserted in the tree before and then other elements would have been inserted, then the tree would have been a bit right skewed, means shifted towards right. So the somewhat similar case has been seen here. So here they have inserted the elements most probably in sorted order, and then we have 4, then 7, then 16, then 20, 37, 43, and instead of what just a binary tree means, a binary tree or binary search tree means, it has just become like a linked list thing, because just as one element has been inserted, then the next element has been inserted as its right child. Then 4 inserted, then in the right child we have 7, and its right child is 16. So this resembles more like a linked list. Now this point says that when all the elements are added on the same side and the tree is skewed wholly towards one side, so this is the situation. And in this case, what happened, that so the height of the tree is equal to the number of elements on the tree. So at each level we are having only one element, so the height of the tree is exactly equal to the size of the tree, this number of elements in the tree, and the complexity is n. Now for example, you are searching for a 43 here, then we have to compare. First we search in a root node which is 4, now after that we are searching for in the right which is 7, after that we are searching east right 16. Now in this way we are searching with 43 and it is done. But while doing this, we have to finally end up compare with all the elements in the tree, and so the search has more or less become like a linear search where we compare with all the elements. Now is it a useful thing? The answer is no, because in binary search what we see, we can discard a one half of the array in each part, but in this so that number of elements which we are processing keeps on reducing, but in this case we cannot discard any element for future. We have to compare with every element. So this takes time, very much long time, which is the disadvantage of linear search. Now for this case also we can accept that there are only 7 elements. What if n is order of 1 lakh of crores? Because in real life conditions the search often almost never occurs with such small number of things. It occurs with lakhs or thousands of data, and performing a linear search on such humongous data takes a lot of time. It may not be days, but at least in terms of minutes or hours. So we cannot tolerate this situation. We cannot accept this. We have to find ways of modifying this situation. We have to find ways of handling this situation. Now here comes the role of AVL tree, a self-balancing tree. What is a self-balancing BST? Self-balancing BSTs are height balance binary search trees that automatically keeps height as small as possible when insertion and deletion operations are performed on tree. Means what happens in normal BST, once we insert or delete elements, we cannot change its height. So whatever be the height of BSTs, we have to work with that, and that is why the problem of all these linked list type things come. But in case of self-balancing tree, if the computer understands that this kind of structure is being created, this kind of linked list type of structure is created, then it will automatically adjust the position of some nodes such that the tree-like structure is again revived. Something like this one. This is a type of self-balancing tree, because there is no kind of linked list type of thing here. After this we come to the definition of AVL tree. A AVL tree named after their inventors Adelson, Velsky and Landis checks that the difference between the heights of the left and right subtrees of any node is not more than 1. Means what? AVL tree is a kind of self-balancing tree. Now how they are maintaining the balance? The answer is given by this particular line. The difference between the heights of the left and right subtrees of any node is not more than 1. If for a particular node, if the difference in heights between the left subtree and the right subtree is either -1, 0 or 1, then the tree can be considered as balanced. Otherwise it will perform some mechanism such that this condition is true. For example, in this tree, in the right side, you can see you can check all the nodes of this tree to see if the balance is there or not. At the root node it is 100 and the left subtree has a height of 1, 2, 3 and 3, and the right subtree has a node of height of 1 and 2. So 3 here and 2 here, the difference is 1. Now for this particular node, here 1 minus 2 is equal to minus. Now so here also it is 2. So now there is a term for the difference between the heights, so which is called the balance factor. So it is an important point of ability. Now what is the balance factor? The balance factor of a node is the difference in heights of the left and subtree of the node. Means that difference which we were talking about, difference between the heights of the left and subtree, this is called the balance factor. It's an important term. Mathematically we can also say balance factor for any node, which is k here, is height of left subtree of that node minus height of right subtree of that node. So in this example, the things they have shown, the difference that they have shown between the heights of left and subtree, this particular thing is called balance factor. balance factor, and this has to be calculated for every node, and the condition that this balance factor is set if it is either -1, 0 or 1, then the tree is said to be balanced. Otherwise the tree is said to be unbalanced. So in this example, you see all the nodes have a balance factor of 1 or -1 or 0. Rest are also 0. So this is a balanced AVL tree. Now let's read the next point. Such a balanced BST helps to keep its search operations limit within an upper limit of O log n, or precisely 1.44 log to the base 2 n. So what we have learnt in the previous points, the structure of BST heavily affects the height and the time taken to search for an element. In case of normal BST, what happens? The insertion order determines the structure of BST, and based on structure of BST, the height also changes, and the height of the binary search tree directly affects the time taken to search for an element. So if such this kind of structure happens, then the height of the tree increases. Actually it is the size, and the time taken is much more than log n, or here is on only. Now if we can keep a structure like this, then what will happen? This structure, linear list type of thing will not happen, and the height will be somewhat manageable. Means after some searches happen, we can discard a considerable amount of nodes for the next search. So the height as the height of the tree decreases, the search time also reduces, and in this type of cases, we have seen that the search time takes O of log n, big O of log n. So it helps, this rebalancing helps us to keep the height of the tree within an upper limit of O log n, or if we calculate exactly, then it will come something around 1.44 into log of to the base 2 n. That is why this AVL tree is generally preferred over normal BSTs, because generally we cannot say in what order the elements will be inserted. So if the linear list types of things happen, then it will be difficult to search or perform operations. And since we have to, after insertion or deletion, we have to rebalance the tree. So insertion and deletion things also happen in O log n time. See, if we insert something here, then also we have to compare with each element. So insertion also takes somewhat around O of n in this case, or in better cases it may take around O log n or something more than that. But in this type of cases, it will take more or less O of log n only, and similar case happens for deletion also. Now we see some examples of AVL tree. This is an example of AVL tree, because you can see here that the root node, the left subtree also has 2 nodes, and the right side tree also has 2 nodes. sorry, this is left sub tree and this is right sub tree. So 2 minus 2 is 0, and here we have plus 1 because left sub tree has 1 but no right child is there, so 1, and here it is minus 1 because left is 0 but right is 1. So this is a balanced AVL tree or AVL tree only, and this is not an AVL tree. This is not an AVL tree. Why? Because root node has 0, okay, left sub tree, this node has plus 1, this is also okay with 0, but at this right sub tree you can see that in its left part has not a single node, and the right part has 2 nodes, so the balance factor is minus 2. So our condition of balance factor is violated here. The balance factor is of minus 2 is there, so our condition of balance factor is violated here, so this is not an AVL tree. So in this case we have to do some rebalancing. Now how do we do rebalancing here? This is done by rotations. The insertions and deletion of nodes to an AVL tree often leaves the tree unbalanced, so the tree needs to be rebalanced. So as we have seen in the previous example, if we insert some nodes into the tree, then only the concept of unbalancing comes, because if you insert a new node to the balanced tree, then the balance may be disturbed. So in this case we have to do the rebalancing, and rebalancing is done by using the concept of rotation. So here the concept of rotations comes. So what are rotations? We just tend to change the position of some nodes in the tree. It may be that of the inserted node or some of their parents, such that the balance factors are adjusted and the state and the balance state can be returned. I mean the tree is balanced again. So this is an example of a rotation. Here in the X node, the A subtree and is much heavier than the B subtree, and in such a way that the the balance factor of X has disturbed to some value which we don't know. So what we do, by somehow we have rotated node X and we have set X as the root node. Now after this, S has been set as the right subtree of X, and link between X and B has been cut off, and B has been linked with S, and A is attached to A, X remains attached to A. So we have the final tree such that this A part whole takes almost 2 levels, B and C contain almost equal level, so both of them have been part of S. Now S, therefore in X also the balance factor has been repaired, and in S also the balance factor, although it has been adjusted, although in S also there was an imbalance, and therefore in S also this has been balanced without any. So there are two types of single rotations. One is left rotation and another is right rotation. So this is somewhat a kind of right rotation, because the links are shifting towards the right. and there are two types of double rotations also, LR and RL locations. Now at first let us discuss the single rotations. Left rotation, which is also known as LL rotation, and right rotation, which is also known as RR rotation. Though they have written them using two letters, but that doesn't mean there is any double rotation here. They are single rotations only. So what is happening in a left rotation? This is an example taken from tutorial's point. So this is the situation when the tree is skewed towards right. Means all the elements in the subtree have been added to the right side. So it is right heavy. So to balance a right heavy tree, we have to counter it using left rotation. Left rotation is somewhat similar to anti-clockwise turn in this case mainly, but you can also relate for other case also. So here we are doing a left rotation on node B, and by this A node will come to the downward position. See, B is here is the center of rotation, and based on this this link AB is getting a anti-clockwise turn, that you can say, and this somewhat represents a left turn. So this B performs a left rotation, and A comes downward, then B becomes the root node, and C remains as it is. So this is an example of left rotation or LL rotation. Now what happens if the BST is left unbalanced or left heavy, that you can say, means all successive insertion have taken place in the left side. So to counter that, we have to perform a right rotation. And here we are doing what? We are performing a right rotation on node B, or you can also say that we are rotating this BC link clockwise, and clockwise somewhat represents a right turn. So about node B, a right turn is right rotation is being made, and C node comes downward. In the so finally B node becomes root, and A remains as it is. So this is right rotation. So somewhat clockwise. In these cases, you can somewhat make it similar to this anti-clockwise and clockwise turns, but these are comparatively simpler cases. There are some complex cases also. It may be difficult to understand it as a anti-clockwise or clockwise direction, but however you can understand that you need to rotate which node, and single rotations are sufficient when the tree is wholly skewed towards one side, left or right, as we have seen here. So if there is such a situation where it is wholly skewed towards one direction, here it is right and here it is left, so here we can perform a single rotation only, to balance this case. Then let's talk about double rotations, which are slightly difficult to understand, but you can, if you observe them carefully, then you can get idea. So first is the LR rotation, which is left-right rotation. So what happens is that if there is some kind of this type of situation, in this case the root node was C, a particular subtree type, and on C they have inserted A to the left child. After that B has been inserted as a right child of A. So there is a zigzag direction. So it follows somewhat a zigzag style. Then first right, then left, and then right. So in this case a single rotation is not possible. So what we do, at first we have to make a left rotation to fix this part. As they have shown here, they have rotated this AB link. On doing so, they have shifted node B here in this position and node A in this position. So the result is this part. So it has skewed wholly towards the left side. Now if it is if such it is skewed towards left side, then we have seen that this can be fixed by right rotation, and so we have performed a right rotation on BC link, and this is the final balance. Now similarly we can also define this RL rotation, or right left rotation. See here in AC, in this subtree, the first node was added as a root, and after that the node C was inserted as the right child, and after this the node B was inserted as the left child of node C. So here also we are getting a zigzag position on to in direction left, right, and left. So what we have to do, here we are performing a double rotation because single rotation will not be enough. So at first we have to fix this BC link. So what this, they have rotated this BC link in clockwise direction. Then on rotating it in clockwise direction, they have shifted the node B in upper position and shifted node C in lower position. So the new tree is A, B, and C. This BC link is done, and now the tree is right skewed or right heavy. Now as we have seen that this kind of situation can be handled by a left rotation. So we have to perform a left rotation along this side. This left direction. So we are rotating this AB link to the left, and we are getting the final balance. Now comes insertion and deletion in AVL Tree. So first comes insertion. Insertion in AVL trees follow the same procedure as that of a normal BST. So what is the procedure for inserting an element in a binary search tree? We compare with the elements already present in the tree and then insert the new element at the desired position. Now in case of normal BSTs, once we have inserted, we don't have to think anything beyond it. But in case of AVL trees, there are some cases where we don't have to think about that, but in some cases such insertion may disrupt the balance factor of nodes and property of an AVL tree may be violated. Now AVL tree has the important property of maintaining the balance factor, so that may have been disrupted after inserting a new element. So for example, the balance factor of any present node which had either +1 or -1, that has changed to +2 or -2 or 3 or something like that. So in this case we have to perform a rebalancing. We have to again adjust the position of nodes such that the property is maintained. Now at first we see an example where insertion has not disrupted any balance factor. So see here, in this example you see the balance factors are either -1 or +1 or 0. There is no 2 or -2 type of case, and so this is an AVL. Now after we have inserted 14, where we have inserted 14 here in this position, in the left of the right child of root. So here the only change which has happened is that the node of 15 which had the balance factor +1, its balance factor has reduced to 0, and there are no more changes. So the insertion has not interrupted or disrupted the balance factor, and this is an example where insertion does not disturb the balance factor. Now we are handling some complex cases, means when insertion has made a disruption in balance factors and we need a rotation. So see in this example, this is a AVL tree. The balance factors are as much as required. So we have inserted 3 in this node, and 3 has been inserted where? In this leftmost side, because it is probably the smallest element. So it has the leftmost node. Now as a result, the balance factor at 2 nodes have been changed, and it is beyond the permissible limit. In node 10 the balance factor is -2, and in node 13 the balance factor is -2 as well. So we needed a rotation. Now a right rotation has been performed in this node 10, or you can say that a right rotation has occurred in this 5 to 10 link. So what happened as a result of this? This node 10 has come one level down. Now 5 has gone one level up. Initially there was no link between 5 and 13. Now there is a link between 5 and 13. Initially there was link between 5 and 8. The link between 5 and 8 has been cut off, and a new link has been created between 8 and 0. Now after doing this, what happened? The balance factor of node 10 has become 0, because there are children at both sides, and after doing this, the balance factor at node 13, that has also changed to -1. So in this case we have seen the balance factor at this node will be -1. So we say that a single right rotation We note 10 as pivot has preserved the AVL Tree property. See, you can also match with the description. After inserting 3, the left shaft tree of 10 became left heavy. So this part is quite left heavy, and so right rotation was made along the 5 to 10 link, which increased the size of the right subtree of 5. So initially the right subtree of 5 contained only 8, now it contains 8, 10 and 11. Now after this we have noted that the 5 to 10 link has vanished and new 8 to 10 link has been created. As a result of rotation, these links have been created. So this is an example of a insertion where single rotation has served our purpose. Now another case when we require double rotation. See in this tree, this is an AVL tree. It has balance factor as per what is required. Now we have inserted 15 in this we have inserted 15 in this tree. Now as a result, 15 has been inserted to the rightmost node. Sorry, not rightmost, the left child of the rightmost node. So as a result, a kind of a zigzag pattern has occurred. 9, 16, 15. Then in this case it is first left, then right, then left. So in this case we have required double rotations, if you can recollect from the previous slide. So at first we have performed a right rotation along this 15 to 16 link. As a result of which 15 has gone one level up and 16 has gone one level down, and so the resultant subtree is now 9, 15, 16. This part is now right heavy. Right. So what we have to do, we have to make another left rotation along this 9 to 15 link, or 9 is made as a pivot and we are making the right. So finally this is the resultant AVL Tree, which is now balanced. Now before these two rotations, the unbalanced node were 7 and 9. 7 also had a balance factor of plus 2 and 9 also had a balance factor of plus 2. After first rotation, the balance factors haven't been changed even. Still 9 contained plus 2 balance factor and 7 contained plus 2 balance factor. After this left rotation, the balance factor of both 9 and 7 has changed and is within the permissible limit. So here double rotation has been required, and so that is balanced. So you can see the description also. The same thing is written. So now it is balanced AVL. Now often it is difficult to get or understand what kind of rotation we must make when some insertion has occurred. So for this we have made a small table. So based on this kind of situation we have to make the required rotation. So see the first case. If the new element has been inserted to the left side of a left subtree, some kind of this situation, then we have to perform an RR rotation. It is now left heavy, so our right rotation will work. Now after this, if the new element has been inserted to the right side of a right subtree, as we have seen here, then it is now right heavy. So we have to perform a single left rotation. Now comes, if the new element has been inserted to the right side of left subtree, which we can see here. So now this is following a right left right zigzag pattern. So to balance this we have to perform an LR rotation, double rotation. And finally, if the new element has been inserted to the left side of right subtree, which is here, then the zigzag pattern is left, right and left. So we have to we have to perform a RL rotation or double rotation. In the next picture you can see how double rotations can be useful here. This part, this tree had a right left right pattern. So first a left rotation has been made on 3 to 4 link, which has made it left heavy, and on that we have to perform right rotation, which has balanced it. Now similarly in right left case, the pattern was left, right and left. We had first made a rotation on 4 to 5 link, so this is now right heavy. So after this we have to make a left rotation on 3 to 4 link, and so the tree is now balanced. Now deletion in AVL tree. Deletion also follows the same procedure as in a binary search tree, and here also, like insertion, deletion of a node may affect the balance factor of the tree. Now you know the cases of deletion in binary search tree, if children contain or not, then we have to perform. Then we have to adjust it accordingly. Only if a node has been deleted, as they are both children are there, then we have to replace this element with the in order successor, which is, if we are deleting this node, we have to replace it with this node value, which is in order successor. So this similar kind of thing is performed in AVL tree also. Now there is only one catch here. Rotation cases are almost same as those in insertion, but the number of rotations may increase. As we have seen in insertion, single rotation can work, double rotation can also work. Means if a case has not been solved by single rotation, then double rotation will definitely fix it. However, if an element is deleted, then single rotation may work, double rotation may also work, but more number of rotations may also be required as per the situation. So we have to be able to be careful. It may take a longer process. So whatever, so let's see the example here. Here we are, from this AVL tree, we are removing this node 4. So as a result, the balance factor of this node 3 has been disrupted, because the left side has 2 levels, but right side there is no element. So the balance factor is now +2. So we are performing an right rotation here, right rotation here. So as a result, this part is now balanced. Node 2 is the root and 1 and 3 are the child. However, the balance factor at the root node 5 has been disrupted, because the left subtree has 2 levels and the right subtree has 1, 2, 3, 4 levels. So the balance factor is -2 now. So what we have to do? We have to again rotate it, and this 5 to 8 has been rotated in left direction. As a result, 8 is now the root node, 5 has come as the left subtree node. And now what happens is that this path 6 to 7 has now joined this 5 node. So it is now a part of left subtree of the root node. earlier it was as a part of right subtree, now it is left subtree of root node, and the root node is now changed 8. Now the rest of the elements are as it is. So this is an example of a double rotation causing deletion. Now there is another example. This is an AVL Tree, and here the node 55 has been deleted. So this is comparatively easier part because this node didn't contain any more children, but it seemed easy, but it wasn't, because after deleting 55 the balance factor at the root node has been disrupted, because the left subtree had 3 levels, but the right subtree only has 1 level, the other 1 children only. So the balance factor now is, so we have to make a rotation. Now what rotation? We are making a right rotation. We are making a right rotation along pivot 40 from, or along this 40 to 50. So as a result, what happens is that 50 has come to the right side, 40 is now the new root node, and the link between 40 to 45 which was there here is now absent here, and the link between 45 to 50 has been created new. As a result, now the balance factor of all nodes has been restored to the previous. Now we come to another example. Here unfortunately the font here is a bit hazy. I don't know why, but I think you can get the basic idea here. Here the tree contains some numbers, I think you can understand 1, 2, 3, then 7, 5, 4, 6, 9. So we have deleted this node 2 from here. Now after this, what happened? This left child of this one has become left side of this root node as per the rule of unity from VST. Now while doing this, the balance factor of this root node has changed, because in left side there is only 1 children, so 1 level, and in right side there are not only there are 3 levels. So the balance factor is now -2. So as a result, what we have done, we have performed a left rotation along this ring, taking the 7 node as the pivot. So while doing this, 7 is now the root node, and then 1 was the left subtree, and it is still the left subtree. 3, which was the root node earlier, has now become the left subtree of the root node. And see, this whole subtree, the whole left subtree of the right subtree of node, which is this part, has now been attached with this node 3. So this is now a part of the left subtree of the root node. Earlier it was the part of right subtree of the root node. Now it is a part of left subtree of the root node. Actually it is the right subtree of the left child of root. So this has come to the left side of with respect to root, and the rest two nodes have just leveled up. So after doing this, we see that the balance factors have been preserved. So it is now again an AVL tree. So this ends our AVL tree class. These are the references from which this slide have been made, or some type of expression could have been given here.
And thank you to all.